All right, so yeah, I'm Grant Smith. Hi, everybody. I really enjoyed seeing Paul's stuff. There was new stuff that I hadn't seen since the last time I'd seen one of your presentations, so it was a good update for me. One of the things I like to emphasize is I feel like it's kind of a very different tack I'm doing here because I almost feel more like a collage artist where I'm grabbing bits and pieces from other people's work instead of like the primary stuff. So I want to give lots of credit here at the bottom. Several people that I've kind of snagged stuff from. You'll see some kind of changes in kind of the style of some of the slides. So I think probably the great guru on Mount Rainier Geology is Tom Sisson with the U.S. Geological Survey. He's down at the California Volcano Observatory. But he's done tons of work up here. I almost feel like, you know, like with the Matrix or something, I want to download Tom Sisson so I know everything about Mount Rainier. Of course, there's Carolyn Dreger. She's done a whole bunch of stuff up here. A few of her slides made in there. And also one of my friends and professors, Bob Lilly from Oregon State. He's done some stuff here at Mount Rainier, but also just with other national parks. He actually made a textbook called Parks and Plates that I think came out like in 2004 or 5. That is actually used in a lot of courses, and so he said I could use some of his stuff as well. So you'll see some of these kind of scattered throughout. And so, you know, kind of my roadmap of what I'm intending to do today is, though we may have some people that are pretty fresh on kind of just igneous rocks and volcanoes and stuff, I figured I would try to just hit a little bit of background, not just assume that, well, of course everybody knows that. And it was partially to kind of put Mount Rainier in context of where does it fit in with other volcanoes, kind of, you know, what do the rocks mean? You know, like I could tell you that mostly it's andesite, but what does that mean? So I try to kind of like build it out that way. I'll talk a bit about some of the volcano hazards. You know, we've obviously looked at a few of those already. And then just some other kind of like side tidbits. Some of these are kind of coming from, you know, things that visitors may ask, and certainly I can't hit everything. We'll have some time for discussion. So that's kind of the idea of where I'm going with this. And so, you know, ideal world, I think, at least in today's kind of teaching, as we try to at least hit a bunch of people with this in like 8th grade, so that may have been a while, and it may not have even been part of the curriculum when you were going through. But how we classify igneous rocks, so the stuff from magma, is really based on kind of texture and composition. We use two different things. So the first thing we really look at is texture. And why that's important is it tells us, well, where did this rock cool and become a rock? And so we really have two kind of big classifications here. We have what we call intrusive. You'll also hear this sometimes called plutonic, which basically means below ground. And when we think about things that are kind of like coarsely crystalline, like big crystals that you can see with your eye. So just to throw one out here that some people may know in this area, the Tatoosh granodiorite. I'll show some pictures of that one in a minute, but like when we see along the Nisqually River here, coarsely crystalline, that's a plutonic rock. And really why it's plutonic is because it was below ground, the heat couldn't escape easily, and so it took a very long time for it to cool down, and that gave it the construction time to kind of assemble the crystals. And so we will see some of that kind of stuff here in the Mount Rainier area, largely not from Mount Rainier. So we're looking at kind of coarse crystalline stuff like that. And then the other side of this is thinking more like what we think of with a volcano, where it's going to be kind of fine grained, something that cooled quickly. You know, the lava is exposed to the air, or even faster would be to the water, like we see underwater off of Hawaii. And so with that, you don't have the construction time, right? You don't have time to kind of get out your Legos and build these big crystals. And so what you end up with is an extrusive or volcanic rock. And we have an awful lot of that here at Mount Rainier. That's mostly what Mount Rainier is composed of, is this extrusive lava flow kind of stuff. And we'll get into the composition here. But kind of the idea with this, comparing the kind of the coarse grained stuff here and the fine grained stuff, is really they're chemically equivalent. The real only difference between those two is did it cool below ground or did it cool above ground. And so that's kind of like our geology CSI toolkit that kind of helps us reconstruct where this rock came from. All right, so there's lots of other textures. The two that I just hit for you are at the bottom, so kind of this coarse-grained and fine-grained. There's lots of other things, depending on which volcano you're going to look at. You can see some of these other ones. A lot of folks are familiar with obsidian. We really don't have that around here. That's a lot more common in Oregon. So like the Native American folks were looking for obsidian. They tend to went to Oregon, and that stuff got shipped far and wide. If you have lots of gases, it can kind of froth it up and make it almost like spongy. So things like pumice that we do get here at Mount Rainier will be like that. You can also kind of weld some of the ash and stuff together and make tuff. And I bring this one up right here in particular is what we call porphyritic, because an awful lot of the lava flow stuff that you see here at Mount Rainier will be that one. And really what that is it's just an adjective. It's kind of trying to say, well, we have two different sizes of things going on. It's kind of like you're taking the fine grain stuff, but then there's like coarse crystals inside of it. And kind of why that's important, again, it's kind of like, well, how do you get these things? Is that the coarse crystals probably started crystallizing underneath the ground where you had time, then you had an eruption, they got brought to the surface and kind of they conveyor belt in the lava, the rest of it cooled quickly. At least that's kind of the ideal model for that. And a lot of the Mount Rainier andesite will show that. And so kind of what I call like the chocolate chip cookie kind of thing, where coarse chunks kind of in a fine-grained matrix. And so you'll see that really frequently around here with the Mount Rainier andesite. So just as a kind of a visual idea, totally different national park, but kind of the right idea, the stuff with like Half Dome and a lot of these places we're familiar with, people climbing on, is really this coarse below ground material. So what you're looking at is stuff that back in the day you're probably looking 5 miles below the surface. This would have been like the magma chamber, but then later on it got uplifted, eroded, and we're looking at the stuff that was way below the volcano, kind of the remnants of that. Of course it's also glaciated and things like that, but that's kind of the idea of this coarsely crystalline material. So this is, kind of the complicated diagram at first, but it doesn't have to be that complicated. This is like the basic igneous rock ID chart that we would use like in the intro class. And really all it breaks down here is we have kind of our coarse grain versus fine grain. And then we have composition. And you'll have these categories like felsic, intermediate, mafic. And really kind of what that's telling you is what is the chemistry of it. And one of the things that we're really looking at is what we call silica. That's just silicon and oxygen. If you get that crystallized all by itself, it's quartz. So a lot of people have run into quartz crystals and stuff like that before. It's a super simple mineral. Well, it serves a very important role. It's one of those things you want to track when you're looking at igneous rocks, because it kind of controls things like, well, how easily does it flow? Is it sticky or is it runny? And it also kind of controls kind of what your rock's going to look like. So it's really easy to get lost on kind of the details. In another class I might get really picky or something on knowing these different minerals. What I would say is just look at this kind of black dividing line. That's kind of the dividing line between like light minerals above and dark minerals below. And what it's kind of telling you is like in this category where we have like granite and rhyolite, with this dividing line being here, most of it's light colored minerals, just a little bit of dark. As we get into andesite, which is more like what we get in here at Mount Rainier, it's more like a 50-50 kind of thing. So it's kind of like about 50% light minerals, 50% dark. As you go towards basalt, which is more like what you get in Hawaii, it's very dominated by the dark minerals. So lots of other stuff going on here. So the silica is increasing this direction. So again, that's just the silicon and oxygen. And so we'll talk about that more in a minute. Also kind of important with that down here at the bottom is it also controls what temperature does this melt at. So when we're thinking, well, what temperature does it need to even be liquid to be flowing and making lava? Kind of what this is letting you know is in a place like Hawaii where they have basalt, is that's lava is generally going to be a lot hotter than, say, something like here at Mount Rainier, or maybe even towards Yellowstone, which is more like what rhyolite is. So those are kind of generalizations, but there's a whole bunch of stuff packed in there. That's kind of why we get really big into thinking about the rocks, because they give all this kind of like information. So just to give you some pictures, instead of just looking out on a chart, I'll just pop all these up here at once. The high silica, so kind of the top of the chart, includes one that everybody's familiar with, at least by name, is granite. So again, the coarsely crystalline stuff that would have cooled below the ground surface. Rhyolite, one of the really dominant rocks that you get at Yellowstone. An awful lot of the Yellowstone at Yellowstone is rhyolite, so some kind of variations there, but very fine grained. But again, the idea is if you pulverize the granite into very tiny things here, you kind of get a uniform color, kind of like that rhyolite. And this is because it's all made of these microscopic tiny crystals. But again, we're tracking the silica, so very high silica, above like 65%. The other end of the scale, what we call mafic, and so this is more like what we get in Hawaii, and we do have some of it here, like with the Columbia River flood basalts and things like that. And the mafic's generally giving you kind of the idea that we have a lot of magnesium and iron. It's lower silica, and so here we have the basalt, fine grain. Kind of hard to show the coarsely crystalline nature of the gabbro, but because it's all dark, you kind of don't get that color variation. But if you kind of got it in the light, you would be able to see kind of the light flashes and stuff off of the crystals that are in that rock. And in between, and this is where it really starts to become important for us here at Mount Rainier, is the intermediate. If you cooled it slowly below the ground, you would get diorite. If you do it more in the lava flows, you get andesite, which is mostly what Mount Rainier is made out of. Ours is a little bit darker than this example. But just kind of like what I was saying before, you see some coarse chunks floating in here, kind of that 2 crystal sizes things. This is actually a porphyritic andesite. Again, that's kind of an adjective showing you some of these crystals were able to form something large, but most of it's kind of a fine matrix. And so how do we get these? Well, here's kind of a little bit of the plate tectonic side of things. Is people may be familiar that we're on the North American plate here, right where we're at right now. And just off our coast, we have this little edge of what we call the Wanda Fuga plate. It used to be a much bigger thing. And it is getting shoved under, it's subducting. Once you get down to about 50 or 60 miles, the easier to melt minerals, the water, which really helps melting, it starts kind of sweating off. The whole thing doesn't just melt like a candle like here, but it starts sweating off some of this stuff. And it's above that you're going to get the cascade volcanoes like Mount Rainier. And with that kind of partial melting, not total melting of this, it's going to be hot enough. Again, this stuff, when it's molten, is hot enough it can cook through the rest of it. Even kind of partial melting, it can go through. And so that's going to give you your magma to make the cascade volcanoes. And it's going to be that more intermediate composition that we're looking at on our slide. So let's look at some from Mount Rainier. We'll take advantage of the administration building here. And these are ones that you'll see along our rivers. Kind of the light colored stuff is Tatoosh granodiorite. That's from kind of old plutonic stuff, never made it to the surface from way before Mount Rainier formed. So you're looking at like 12 to 14 million years old. Very durable. You'll even see the contact on that, say, going up towards Comet Falls. Like the lower section, you'll be on that stuff, and then pretty soon you switch over to more like the Mount Rainier andesite, which is like the dark grays and the reds being where they have a little bit more oxygen in there. And in general, what we can find is that Mount Rainier is about 500,000 years old, so considerably younger than the Tatoosh granodiorite. Those are the oldest flows we have. And certainly a lot of the building of that was just within about the first 200,000 years. It's continued to be active, but to give away one of my things with this is volcanoes, at least like most of us, tend to be more active in their youth and then kind of slow down. At least that's true for me. And that's kind of the story of Mount Rainier too, is that it was very active early on, and it's still active, but not as active as it was kind of like in its early days. So those are two of the big ones to have in your kit for understanding Mount Rainier. Now, I also like to point out one of these because people a lot of time will look at the granodiorite and say, hey, that looks like granite. And I get it, they're close. They're both coarsely crystalline, but they're not identical. And a big thing, hopefully I chose one that was like really stood out here, is true granite tends to have more potassium feldspar, kind of the salmon colored feldspar, and it tends to be a lot less available in granodiorite. If anything, granodiorite's almost like this bridge between like the intermediate to felsic part of the thing. So we're already starting to split out that chart we've already looked at. And really what this is these are just two different mixtures. That's all the rock label means. It's kind of, you say that label and it's like, well, I have expectations. I often make this analogy. It's kind of like, well, if we know our salads, and if I order a Caesar salad and then somebody gives me something that's like spinach and bacon and stuff like that, I might be a little bit grumpy about that, right? Well, it's kind of the same thing, at least for geologists, is when we say something like a granite or granodiorite, we kind of go back to those charts. It's like, I expect this, and this to be there. And it's also why sometimes when we go to our favorite hardware store, and like everything that's coarsely crystalline is called granite, it kind of gives us the twitches. It's like, well, that's really not true. Like, there's no such thing as black granite. That's probably like the gabbro we were looking at, right? So it's kind of, geologists are really specific with what granite is. I think in other kind of contexts for, the regular world, granite's used a little more liberally for just coarsely crystalline stuff. But especially at least in the geology thing, it's a very different thing than our granodiorite. So this is kind of my, Ted Turner colorized version of a graph from, or a diagram from the 60s from Dwight Crandall, Rocky Crandall, one of the USGS geologists that did so much of the early work here on lahars, on the geology. And those rocks that I was showing you in the admin building, those two, essentially show you the main colors on this diagram. So I put it into my paint program and stuff. The granodiorite is the pink on this diagram. So in a way, it kind of forms the platform from this earlier period of igneous activity, and then Mount Rainier kind of came through and then formed on top of that platform. So it's a good, stable, durable platform. Yeah, it's like I was mentioning, some people outside, it's like our tack-ons here that I don't have nearly as much in here, is this stuff on kind of this north side here, like the Ohanapakash Formation, Stevens Ridge, some of these different things. All of these predate Mount Rainier. They're kind of up on the edges. So we even see some of that stuff going down Stevens Canyon, or we see some of the Stevens Ridge, which is like the ash deposits, or tuff deposits. So there's a lot of those things out there. I didn't really concentrate as much on those with this, but they are an important part of the geology story here. And just kind of going down here, this will also show you, at least in terms of the lava flows, we have like Pan Point. It's kind of been carved out into the Paradise Valley, but like this is more like Mazama Ridge kind of stuff in this area, so some of that kind of extended around. But the Tattoos Range has some of its own lava flows on top, but especially the core of that really is the granodiorite. All right, so part of why I was kind of focusing on composition and silica was because that's going to be an important control on how a volcano behaves. We may have some folks here that have been to Hawaii and seen that stuff, or you've at least seen it on video. And this is a generalization, but generally we would think of those as being less violent eruption. Violent being a very relative term. But a lot more common is you're going to see kind of like the fast-flowing rivers of lava. across the open landscape, not so fast, but we see those kind of tubes of it where it's flowing quickly to the ocean. So low silica kind of is the gentler side of things. And as we get more into the Cascades, though there is variation in composition, I'll go a little more andesite. Like Mount St. Helens tends to be kind of a little more silica rich. You know, just like 4 or 5% richer in that silicon and oxygen than Mount Rainier, and that pushes it into the range where you have dacite. So not quite to rhyolite, kind of again, kind of an in-between thing here. But that one tends to be much more explosive. And so it's kind of, okay, what are some of the reasons behind this? Well, we can plop all this up here. I'm just going to throw all these at once. In that, those compositions we were looking at are kind of like the felsic, intermediate, mafic. Here's your silica content again, so we're increasing to the left. We already talked about the melting stuff. Well, this is the thing that controls the stickiness. You know, how viscous is your lava? How viscous is your magma, even when it's below the ground? And especially if you throw in some gases and some water, what you're going to tend to see is, as you go towards kind of the left side of this chart, kind of the intermediate to felsic, more explosive eruptions, whereas if you're more towards the right, like lower silica, kind of gentler eruptions. Again, water is weird. If you throw it in there, it's almost like a wild card that you can get explosive stuff due to steam and stuff like that. But these are generalizations that we can make based on kind of the composition. So I kind of look at this as the thickening agent. So I'm sure I have some people that, you know, cook out here. If I'm making gravy for Thanksgiving and it's too runny, what do I put in there? Flour, right? Or starch and arrowroot powder. There's various different substances that can do this. That's kind of the way silica is, the silicon and oxygen in magma. So when we look at a place like Hawaii, where we're lower silica, I often think of it more like chocolate syrup. You know, it's got some substance to it, but it flows easily. It kind of wants to spread out. Whereas when we look more towards the Cascades and even towards Yellowstone, you're thinking about it's so thick and goopy. We've added more of that thickening agent in there. It's more like oatmeal, right? It's like you can flip it over, it's going to hold its shape, it's not going to flow easy. And that's kind of the role that the silica is playing in this. And so that's also going to influence your shape of your volcanoes. So again, we get a lot of comparisons with Mount Rainier with other volcanoes that people may have seen. I put up one of these boards for one of my interpretive programs, just saying people, you know, hey, have you been to another volcano? Which one? And with all of our travelers and stuff, pretty soon, you know, we have dozens of them up there. It's truly amazing how many different volcanoes people that visit Mount Rainier have seen. Well, what we're looking at here, if I remember right, this is Mauna Kea in Hawaii, and it's one of those that is made by that running lava, right? So it spreads out. You know, just think about pouring your chocolate syrup out on the table. It wants to spread out. You have done over time making a mound of it. And that forms what you call a shield volcano. And it really is mostly lava. Not going to be like us here where we're dealing with a lot more kind of variation with like ash and pumice and ashfall and different things like that. So it gives you a very distinctive volcano shape. It's one of the biggest volcano shapes. It's very, very broad. And so kind of in a summary diagram here then, is shield volcanoes tend to be the broadest. We're going to be adding some more in here, but they tend to be, at least in terms of your slope dip, on the more gentle side. You're usually looking at only about 8 degrees. We'll put some other ones on there for some comparison here. So very broad and gentle. All right, so if we take that same kind of like low silica lava, and we do have some gas, we actually make our steepest volcano form, which is the cinder cone. So one of the most famous one is Puricatine and Volcano, which in Mexico. This is one that was in a farmer's field. You always knew it was a poor place to grow corn, and then he came out one day and the volcano was forming there. And I think it was over the course of like 9 years, we basically saw this thing live and grow, and that was kind of the end of it. But we certainly have others around. There's some down in Oregon on the Newberry volcano. There's like 200 of them down there. One of the things that really controls this, it's almost like you're making a volcano out of popcorn, right? Is you're flinging lava into the air, and it's cooling, maybe kind of like frothy. Some of it may weld together, but it's almost like trying to make a pile of sand. You know, like you're trying to do it inside of the hourglass here, or it's on a beach or something like that. Is you start out, and it's kind of like you're building your mound, and then you get to that point where it's not getting any steeper. You can make it bigger, but it just keeps on sloughing the stuff off the side. That's what we call the angle of repose, and so that's something that applies to dry stuff. If you have water, and then you have stickiness. But that's going to be kind of the size, or the angle that you can do a cinder cone at. And so one of the more famous ones, at least in the National Park Service, is going to be Wizard Island out at Crater Lake, kind of the most recent expression there of Mount Mazama. So that kind of like steeper form, right? With that, you're looking more in the range of about 30 degrees, so much steeper than say like that shield volcano that we see in Hawaii. But again, these aren't mutually exclusive. You can actually see it like gas vents and stuff on a shield volcano. It's not that the cinder cone is kind of superimposed on that, so I don't want to make it sound like you just get one or the other. All right, let's move closer to our neck of the woods here. And thinking about Mount Rainier, we do have more of this intermediate composition, so it's thicker and goopier. It's not the thickest and goopiest, but because you do have kind of this explosive nature sometimes, is you alternate depending on whether you have trapped gas. Do you get lava flows, this is when you tend to have less gas, or do you have kind of like the more explosive events, like what we saw with Mount St. Helens, and it alternates. And so you'll see that these are called composite volcanoes. Sometimes you'll hear them called stratovolcanoes that refer them to the same thing. It's just that it's got layers, kind of like plywood is a composite, right? And so with this then though, it's like depending on where you're at, you're going to get different layers of different materials, and yeah, it's going to include some more mud flows. It's going to be part of it. It's going to be kind of a less stable layer than maybe some of the others. And so that kind of makes for a more complicated story in terms of our volcano and how it's going to behave sometimes. So yeah, a good example from Tom Sisson's stuff is like kind of the Willis Wall stuff. This is just lava flow after lava flow here on Mount Rainier. And again, it does vary some, but I'm trying to remember one of the stats. It's something like in the ballpark of around 90% of all the lava flows at Mount Rainier are andesite. It's maybe one of the more consistent ones in terms of the Cascade volcanoes. There's been a few of them that are dacite, kind of more like Mount St. Helens, so they can kind of vary their chemistry over time. But if you're looking at it and you're guessing andesite, that's probably a pretty good bet. All right, so there is our composite volcano, kind of our strato one. And so you'll see here is this, in terms of its steepness, and again, this is variable, this is a, kind of depends on your volcano, generally about 10 to 20 degrees, and more kind of not as broad as say like the shield ones. And it's because it's this stickier, goopy stuff that doesn't flow as well, right? So that's kind of where we come back to the composition side of things. And then the kind of the final one we can add in here is this is one from Tom Sisson again, well, actually from Cyrus Reed. They've done a lot of study of volcanoes up in Alaska because they have so many of them. Here you're starting to see one of these lava domes form. Probably closer to home again, one of the more famous lava domes we have is the one that's going on inside of Mount St. Helens. And there's some really great time-lapse video. I don't have it as part of this, especially like from the 2003 to 2007 from the USGS, where it's like you see this kind of building up and crumbling and building up and crumbling. It's very slow. It's really something you do have to do with time-lapse because it's like turning a rock before it even gets to the surface. So you don't have kind of like the lava flows that are easy to see here, but it's like it's kind of building and reconstructing some of that wound in there. And so we do have some examples of that here. Again, this is one of Tom Sisson's kind of on the Liberty and Ptarmigan Ridges. you can kind of look at some of the layers in here and kind of the analysis of this is that was some lava dome formation here on Mount Rainier. So we get some of that as part of the component too. Since that's pretty much all lava, it's going to be kind of at the high end of what you see for the composite volcano, so about 20 degrees. It's going to be about the steepest stuff that you can get out of kind of the stickier, intermediate to borderline felsic lava. All right, so that maybe puts it into some context with some of the other volcanoes that people may be familiar with. From here, after I go to slurp the water, is we'll look at some of kind of the hazards, some of the ash, and kind of build the story from there. And stuff like that, then you can get some of the obsidian, whereas like, yeah, most of the stuff up here in Washington State is more just like a uniform andesite. So it's kind of, can you break off a fraction of that? So.
I did have someone tell me that there is actually over by Yakima some blue obsidian.
Oh, nice. That's one I'm not familiar with.
Yeah,
That's
it's
like,
some property that belongs to Nature Conservancy. I was there with one of their people once, and they just acquired it and had surveyed it, and they said, oh.
yeah, so there we go. There is some in Washington State, just not as much as Oregon.
Yeah.
All right, well, looks like we're rolling again here, so let's go ahead and dive into some of these. Some of you have kind of picked up on some of the stuff in the diagram. Again, another great U.S. Geological Survey kind of diagram of some of these different volcanic hazards. I'm going to be looking at some of these, so like ash falls. The hot ash flows, that's the same thing as some people kind of picked up as the pyroclastic flow. So again, two names for kind of like the same thing. I'll mention a little bit about some of the mud flows. You know, we've looked at some, at least some of that kind of in Paul's talk. But we'll also kind of talk about lava briefly. Again, I always like to say it's not as fast as you might think. And I also do like to mention volcanic gases, because that is one of the things that they monitor here to kind of check out the health and such of Mount Rainier. So that's kind of our laundry list for now. We'll break it down into kind of different parts. So, all right, ash falls. You know, certainly we got a lot of that out of Mount St. Helens. That's one of the things that we see as being the most recent, truly documentable volcanic events here at Mount Rainier. So usually when we're talking with like visitors, when's the most recent? You're usually, depending on how we round it, saying anywhere from 1,000 to 1,100 years ago was the most recent stuff. That was some ash fall. It looks like it was more towards kind of the northeast side of the park, so maybe thinking more out towards like Sunrise, was it Summerland? Some of this stuff looks like it backed up a little bit, kind of to the middle part of it, so where they have that ash mapped out, but not so much on kind of the south side of the mountain, so kind of a little bit directed in that way. So that's the stuff that we can truly document. I'll go ahead and throw it in here. You can run into lots of literature, comments, even charts and diagrams that suggest there was some stuff in the 1800s. That's a big question mark. If something did happen in the 1800s, maybe it was just steam. You know, if it's steam, there's no like physical evidence left, right? Just like steam just blew away. But there's something like 14 different accounts of like that, kind of like scattered throughout the 1800s. And you know, a lot of us have been around Mount Rainier on kind of the bizarre days where we see clouds forming on top. You know, if it's oriented the right direction, did somebody misinterpret that and think it was like the volcano waking up? You know, we get that at like the info counters and stuff, people nervously looking up at the clouds and thinking the volcano's waking up. And you know, it was reported in newspapers, so maybe it was a good way to sell newspapers, different things like that. I don't think that we can totally discount that stuff happened in the 1800s. It's just we don't really have any evidence of anything happening in the 1800s than just those accounts by people that like weren't geologists. So I waffle on that one, and that's kind of why we go back to this more like 1,000 to 1,100 years ago stuff where we actually have rocks. Part of what we do get from Mount Rainier does include like ash and pumice. So pumice is kind of the bigger chunks, kind of frothy, almost like sponge-like. You will run into some stuff if you're kind of going through the literature from different time periods, where especially some of the people, Rocky Crandall and some of the people who were working with him, thought that they had some like pumice and stuff from the 1800s. And it's kind of one of those complicated geology things. You know, normally it's like you do it like a layer cake and the youngest stuff is on top, right? It's like that's just kind of stratigraphy. It's like oldest stuff's on bottom, youngest on top. Kind of what they figured out was that pumice they were looking at, though it was on top, was actually like washed down by like slope wash in the sunrise area. So it was on top, but it was kind of like redeposited. And so they're actually able to figure out that that was maybe from some of the stuff that was more like about 2,000 years ago, which was also an active period like 2,200 to 2,000. So this is where it gets complicated. It's like we're always trying to like grab the literature and kind of like build our stuff out. And especially Tom Sisson was one of these people that kind of helped dispel kind of a misinterpretation. You know, science, we get better tools and stuff like that, and sometimes we have to modify our take on these things. Pyroclastic flows, potentially here at Mount Rainier, maybe not as much as some of the other Cascade ones. Again, it doesn't seem to have as many of like the big explosive events, at least recently, as say like Mount St. Helens. But again, you know, as soon as you make a true definitive statement like that, well then Mother Nature will prove me wrong and the next one will be explosive. But this is a hot cloud. It's like it's still where the stuff can like fuse together. And it's trying to remember about like 600 degrees Celsius ballpark. So it's going to be like an oven, you know, coming down. It's going to roast pretty much everything in its path. We have some really good examples of these from the Philippines. This is part of what happened with Pompeii, especially with Herculaneum, where they've done tests of like throwing pig bones in a fire and kind of looking at the trauma, and they figured out kind of similar things with the people there. But they do obey gravity, so they tend to hug the river bottoms. So kind of like what we talked with, getting away from like debris flows and stuff like that, is get away from the low spots, kind of hike uphill. That would be kind of your best bet, but hopefully with the monitoring and stuff like that, none of us are anywhere near the volcano by the time it would do anything like this. But we do have evidence that some of that has happened here, so part of the Oklahoma includes some of these pyroclastic cloud deposits, so kind of this fused ash. Lava flow, so especially my young junior rangers that come up are always kind of disappointed. They want to see like lava flows, you know, flowing down the side of the mountain, burst the volcano and stuff like that. And again, this kind of gets back to what we were talking about earlier with composition. Fortunately, I was about 4 years ago, the lead of Hawaii Volcanoes National Park was here for a conference, like in this room, and he gave like a presentation. And even kind of the runny stuff in Hawaii, he was saying it's like if it's on the open landscape, so not like one of these insulated tubes where it's going by like a rocket, but like actually creeping across the landscape, only about 3 miles an hour. Those of us have been on a treadmill know what that is, right? Like 3 miles an hour, you know, it's kind of like this. And so it's like if the lava flow is coming, even in Hawaii, you're probably going to be able to outrun it. And our stuff here is even thicker and stickier and goopier. It's more like that slow lava dome stuff that we talked about with Mount St. Helens. So I guarantee you, everybody here in this room would be able to outrun any lava that would come out of Mount Rainier here. So it's an unstoppable thing to some degree, you know, when you run into it, but it's like, it's just, with all the other possibilities of Mount Rainier, it's probably one of them that we worry about the least. All right, other bizarro kind of things that people notice in lava is sometimes you kind of get this like organ pipe looking structure, columnar joining. Yeah, so yeah, this is along the Deschutes River, especially with the Columbia River flood results, kind of way earlier than Mount Rainier again. We see some really good examples of this. And it can happen in lots of different lava types. So many of our great examples of this are in basalt around the world, but it doesn't just happen in basalt. It's not unique to that, and so we'll get into kind of why. So a great example down in California, Devil's Post Pile. showing really good examples of kind of that jointing. And what this is it's a result of cooling. Lava's hot, right? Hot things expand. So when you want to cool it, you want to turn it into rock, it has to lose some volume. So it's kind of like you're taking your stuff and stretching it kind of uniformly in all directions, right? So it's like stretch, stretch, stretch. What's going to give you an interlocking shape without like big weird gaps and stuff like that? So in a way, it would like to form circles, let's going back to classical philosophy, circles are perfect, right? But they're not perfect in terms of interlocking. I don't know, there's probably some math term for these weird curved triangles that you would get between the circles, but it's not interlocking. It's not going to deal very well with kind of dealing with the tensional stresses. You're trying to lose, I think it's about like 5% of your volume as this stuff cools. So instead, your kind of interlocking pattern is it going to be, because it's going to favor hexagon, so I'm just kind of going beyond this here. That's kind of like the simplest geometry that kind of like is interlocking and is giving you kind of stress relief in all directions. And I ran into a thing a couple of years ago because we tend to associate this structure with like honeybees, right, with like beehives. My understanding with that was like, yeah, actually the bees are not like mathematicians that we love hexagons or something like that. Is they're trying to do tubes to start with, but as the wax and stuff dries, it's losing some of its volume and you start making this like hexagonal structure. So it's kind of a weird like geometry thing, but it's really just due to cooling. And so we can get this in lots of different types of lavas. And we get it in some of the andesite here at Mount Rainier in some situations. So a lot of text there, and we need to have another drink of water. All right, now the interesting thing is so much of the time when we're looking at this stuff with like the Columbia River flood basalts, a lot of other things, is the columns are going vertical. What people will see in different areas around Mount Rainier, sometimes you see them going sideways. So it's kind of like, okay, what gives here? What you're actually looking at is this is lava that flowed down between glaciers. And so the glacier was like right beside it, so you have like this big cold sink, if you will. And so it cooled in the direction of the glacier, so you end up with these columns going sideways. So you especially see this easy going up towards sunrise. There's like one pull out where you can see this one. But there's several examples of this around Mount Rainier. And so again, one of the great places to study this is Alaska. They have lots of glaciers up there too. And kind of what they found, and this is something that, again, Tom Sisson brought to the table, at least for Mount Rainier, is that though you might think that lava is amazing and hot and it's just going to go like a hot knife through butter, is that, well, if you cool it down, it's turning into rock, right? So it really can't flow that direction. The easiest pathway isn't to go plowing right down through the middle of the glacier. The easiest pathway is where the snow, the ice is thin. So we have like an interpretive sign out here on the Trail of Shadows that kind of talks about this, is it tends to go down the ridge lines instead of right down through like your glacial valleys. And with that position, while you're going down the ridge line and like your glacier's off to the side, that's going to give you kind of this orientation where this lava flow went down the shallow stuff to rock. So it flowed out this way, and then the cooling is going to be sideways. And so that's kind of why we see some of those interesting orientations to our columnar stuff here at Mount Rainier. So yeah, that's part of the Rampart Ridge story as well, kind of following that ridge line kind of stuff. All right, so I have just a little bit of stuff talking about the volcanic mud flows. So to some degree, these almost tie in like the glacial outburst floods. You're kind of talking about a lot of similar mechanics here, but I'll kind of look at more maybe the rock side of things on some of this. The term you'll hear sometime for these is lahar. That's actually from Java, Javanese. Basically a mud flow on a volcano. And that's a term that's used all over the planet, specific to volcanoes. There's some kind of interesting kind of characteristics to this with how the ash interacts with the water and how it behaves and things like that that make it nice to have this unique term. I will warn you on this, and it's something that our folks at the USGS have kind of come up with, is though in other places on Earth, pretty much any debris flow on a volcano might just be called a lahar. Here they've tried to separate it into two different things to kind of avoid like a cry wolf thing, is that the smaller debris flows we're just going to call debris flows, and only the really big ones, like when the volcano is active, the ones that could potentially reach much further outside of the park, that's what they're kind of calling lahars. So people may have run into like the lahar warning systems, things like that. They're trying to kind of make it so if we say lahar, everybody takes it really seriously, and instead of calling everything a lahar, and then people think, well, the last one wasn't that big of a deal, right? So it's kind of getting the right mentality. Okay, so let's kind of look at some of this, and this is where we overlap a little bit. These are probably the biggest day-to-day hazard concern because they're the least predictable, especially the volcano waking up and doing all those volcano things that we've talked about. We do a lot of monitoring, and we figure we're probably going to have, weeks of warning. The lahars are a little more unpredictable, though, again, if the volcano is active, they're probably going to be bigger. And part of what this gets into is some of the rock isn't strong anymore. Especially with volcanic activity, you have the gases and the steam and stuff like that kind of coming up through different vents and stuff like that. And essentially you're chemically kind of breaking down the rock, you're altering. It's what they call hydrothermal alteration. And so especially people up in like the Paradise area may look and you see a lot of these kind of like orangish rocks up there. That's the stuff that's hydrothermally altered. It's kind of like taking our kind of like medium grade andesite, and you pass a whole lot of steam and gases and stuff through it, and it reacts, and it breaks a lot of like the feldspars into clay. It's not as strong as rock anymore, and that's one of the big concerns. Like, well, I don't want to have a volcano made out of kind of weakened material. Sometimes I'm tempted to call it as like now the rock is kind of rotten, but in one of these conversations I've seen like Tom Sisson kind of a little uneasy with that, because rotten almost makes it sound like it's continual, like it's continuing to degrade. And it's really that alteration is something that happened in the past. It's not like continuously happening. You're going to get weathering on it as well. Of course, we have the glaciers, massive source of water. You start adding in like volcanic processes, and we have like heat that can melt the water. And all these things are going to kind of combine together before you can get this like thick slurry. It's almost like wet concrete that can come down your river channels, raft up big boulders, and be extremely damaging. So just a little picture of the Nisqually just looking kind of muddy. But if this was a lahar, it would expand, it would flow out over the banks, depending on the size of it. And so now you have all these boulders that are battering rams, knocking down trees. Some of the early work by Rocky Crandall back there in the 60s, he worked for like 10 years. He won like one of these big awards for like this great paper on the lahars and stuff like that, because he looked at a lot of the hazards and what do we do if these happen. I don't know if that's still part of the current things. Some of his ideas at the time then was maybe we need to start drawing some of the dams down outside of the park and stuff like that to maybe help contain some of that stuff. But of course the biggest one, especially for folks familiar with Sunrise, we talk about this a lot over there, but we can talk about anywhere at Mount Rainier. The biggest one of these lahars that we know of is called the Osceola mud flow. It was during a period where the volcano was being active, so we had volcanic activity going on. We took some of that hydrothermally altered rock that was weak, and maybe this is a little bit similar to what happened with Mount St. Helens. I don't know 100% sure on that one, but you basically broke off a big chunk of the mountain. It sloshed over some of the ridges there near Sunrise, parted around there, went down the White River, and flowed all the way to Tacoma. So in a lot of ways, it's like our worst case scenario of what can happen. So we look at that and say, okay, that's really bad. There are some others out there, but especially for our towns that are nearby, that's a big concern. So some of them like Ording and Puyallup and stuff are in the pathway of these. So I know like the school kids have to go through the hard drills, so if the sirens go off, which way's uphill? And they'll want to be trying to figure that out on the fly during a big event. But yeah, you're looking at 212 square miles of deposits just from that one mud flow. So all of this stuff here is Osceola mud flow deposits next to that river. But we have more recent ones, and some Native American accounts with this, like the Electron one, which came down the west side and went into Ording. We have Native American accounts from that from about 600 years ago. We think this is probably the Electron mud flow. And yeah, made it a very not great place for growing a number of things, you know, until you could develop soils and things like that. But that's kind of right there in the pathway of these. So especially for the folks that are working on the warning systems, this is the stuff that we're trying to broadcast out to the public and kind of be good partners with the nearby towns. Especially when we look at a map here, the yellow is the Lahar hazard zones. And really what this is like, look at all the different rivers that are coming off the glaciers on Mount Rainier. And all of those things in the yellow are potential pathways where these could go. My understanding is with like the lava flows and stuff like that, those would all be very localized. So like kind of the extent of the glaciers is a good approximation for about how far the lava goes. The Lahars are more like the tentacles of the octopus here, right? It's like they're going to go much further, reach much further out, and a much bigger concern for kind of the whole region than stuff that just may happen largely within the boundaries of the national park. And yeah, so lava flow is not a real risk for the folks in the population centers.
What's the purple? I can't read the label for it.
The purple, post-Lahar sedimentation zone. And the green, and it's kind of too fuzzy.
Duwamish, probably.
Valley. Yeah, so.
What does that mean?
I think it's stuff that it's like, as like the river runs through and stuff like that, maybe it's kind of like beyond the flow, but it's almost like maybe like one of the aggregation things. Does that sound reasonable?
Yeah, I think it's post-rain, it re-washes it further down.
Okay, yeah, so that's kind of what I would
Yeah,
do.
it's like that.
Okay.
Thank you.
All right, so one question I think is kind of an interesting one, it's kind of challenging, is this question of whether Mount Rainier was taller in the past. Yeah, probably. How much taller is really hard to assess, and so one of the things I saw with this actually made it into some of our literature, and you know, as soon as you write it, then people like latch onto it, you know, won't let go kind of thing, was they looked at kind of like the dip of some of the lava beds, kind of a simple thing, and it's like, well, if we project the dip of those lava beds up, how high of a peak would that make? That makes it about 16,000 feet tall. Was Mount Rainier actually that tall? I don't know. You know, mountains are complicated. How good of a reconstruction is that? You know, we have multiple like angles on Mount Rainier right now. But, you know, we did remove some of the top of this from that Osceola mud flow. So some of it's been rebuilt, but I think I will leave that as a lawfully thing. Yes, it was probably taller in the past. How much taller? Not sure. So very uneasy about like that 16,000 foot projection. That seems to kind of fall in our favor. All right, and finally, we do get gases. That's one of the things they monitor here at Mount Rainier. It's part of the kit of figuring out what happens with your volcanoes. It's almost like going to the doctor, right? We have to go through all of our different tests of, well, what's the baseline? You know, what's normal for me? And it's kind of what our folks from the Cascade Volcano Observatory have done, is they're trying to figure out what's the baseline for Mount Rainier, what's normal? Because then when it changes, that might be a red flag, right? It's like, oh, it's putting out more of this gas, or something like that. One that is well known from Hawaii is what we get as fog, basically volcanic fog, just like smog is kind of a smoky fog. But this is highly reflective stuff. Sulfur dioxide is highly reflective, so it shows up really well on visible things. But it's like you combine that with water, and it makes sulfuric acid. And so they have warnings there on the Big Island where you're getting a lot of this fog that especially people with asthma and things like that need to stay indoors, just kind of like what we do in the big cities when it's like a really bad pollution day. Well, that's just one of the examples. I mean, the most abundant gas that comes out of the volcano is actually steam, so just H2O. That's one of the things that we can track. Of course, there is CO2, and since we're kind of hit a little bit on this, on some of the climate change stuff, sometimes people want to be blaming the volcanoes for more CO2. They're only about 1%. We monitor the volcanoes now, so we can't just like throw that out there and blame the volcanoes for the CO2 in our atmosphere. They're a contributor, but it's pretty minor. There's our sulfur dioxide. You can also get hydrogen chloride, way more stuff even than what I have here. But so many of these things, you combine them with water and you're making an acid, right? So it's pretty nasty stuff. And one of them I love, I don't have the video for this, but we even have to remember, you know, just CO2, that's what we put in fire extinguishers, right? Because it smothers the flame. It's heavier than air. So if you're near a volcano and it's starting to put out more CO2, now you need to be concerned about the swales. Any kind of a dip on the landscape that can hold that. And the video I've shared sometimes in my class, I think this is near Kilimanjaro, was that the locals there knew to stay out of these depressions. I think they called it a Mizuku, like the deadly wind or something like that. And it was because the CO2 builds up from here, and if kids run through there, they can suffocate. The adults are still tall enough that they may be above the layer, so it's kind of like this mysterious kind of like, why are the kids dying kind of thing. And it comes back to CO2 and the suffocation hazard. So that's another one of the things that we have to be concerned about. Just to throw this out here, more like an OSHA idea, is that the air in the room we're breathing right now is about like 21% oxygen. Even reducing that a little bit, now it's almost more like you're up on the side of the mountain, it's getting like hard to breathe. Once you get down around like 14%, this is the stuff where people degrade really, really fast. And so we run into this in places, you know, like grain silos, you know, due to fermentation, you know, we build up and kind of use up the oxygen or in sewers and things like that. So we have to be extremely concerned about that around a lot of volcanoes too. Kind of one of these invisible killers, if we will. All right, and then finally, some of the other tidbits. There's a lot of versions of this diagram that are coming out of the USGS. Kind of really the history of volcanic eruptions in the last 4,000 years. And I always look at like Crater Lake, it doesn't show up. Forming at Paradise, and they come down Stevens Canyon, and you can see the peak of the mountain from there. So sometimes it's just like 15 minutes of driving would save a lot of people a lot of grief. It just depends on the day. I say those especially like on the kind of the partly sunny days when Paradise is like totally socked in. That's a really good time when you can see that. Does that mostly answer the question? Yeah, okay. Ready to go? Yeah. All right. So yeah, we're almost done here. One of the things that you know, I really do try to stress is this is a very monitored mountain. So we've kind of hit these 2 points as we've gone along. Especially the 1894 to 95 is the one that seems to be reported the most. But again, if that was just steam, we don't have any other evidence of it. But the USGS does have monitoring on this mountain. We have seismic detectors out. I forget exactly how many. The weird thing with that is, and kind of a Mount Rainier kind of quirk with this is, you probably know like 97% of the mountain is designated as wilderness area, right? Part of the trick with that is no new permanent infrastructure in the wilderness area. So, and that would include seismic stations. So my understanding, if I have my stats on this right, is they have to move their seismic stations every 7 years so it doesn't become permanent infrastructure. And I think there was a desire they would have even more of them out there, and I think if it did start waking up, they'd probably be able to make the case to get more of them out. We do still have evidence that the volcano is active. I mean, we do have like the warmish springs here in Longmire, the hot springs over Ohana, there's fumaroles and ice caves up the top of the mountain. So we know this is still an active volcano. In terms of the earthquakes, we get them. Most of them are small enough that people don't feel them. And it's more kind of like the mountain shifting and settling and stuff like that. Nothing that's really suggesting that magma is on the move. There's a particular type of earthquake that they call a harmonic tremor. If you look at a seismogram, it's kind of like we keep on getting the same earthquake again and again, like same size, same kind of shape and stuff like that. That's the one that the volcanologists look for that basically say that magma is moving. We don't have any of those right now. And of course, in the big plate tectonics picture, we have the one diagram of the plate going underneath the other. We're still in that setting. So pretty much everything here suggests that this volcano will wake up again. It will have some type of an eruption again. But if our lessons from Mount St. Helens hold true, we will have weeks to months of warning. And in that case, this whole park's probably going to be evacuated, and so many of the how do I escape the dangers of the volcano get reduced down to maybe thinking about the lahars and things like that. So, yes, all kinds of other stuff. They also have GPS. So a lot of us use that for navigating the trails. Some of this really good scientific GPS is really good at elevation. So if the volcano starts waking up, you tend to like get swelling, and so the landscape raises. That was part of the Mount St. Helens story, is it got like this gigantic bulge on the north side, very obvious. I have some pictures in here if anybody wants to see them. You know, I just kind of put them at the end, just kind of like a rada or something, really not part of the presentation, but that is part of the equation. And of course, the monitoring of the gases. So I think that's pretty much everything. Now that I've run through the tape multiple times. Yeah, thanks for letting me be here. Hopefully I've kind of built a little bit more on the knowledge base of at least some of the geology here. I know it's not everything, but there's a lot going on here too. But yeah, I'll be glad to at least take my stab at any other questions that folks have too. So thank you. Yeah.
Yeah, thank you for your talk. I just want to clarify what triggers a lahar, because you said it can occur with or without volcanic activity.
And that's a great question. Especially if you have the volcanic eruption, you know, of course you have the lava and the heat and, you know, melting of the glaciers. That would tend to make the biggest ones of them. So those are kind of like the really clear ones. The electron mudflow, the one about 600 years ago, we don't think that was from a period of volcanic activity. With that one, we think it was probably some of that hydrothermal rock, the stuff that was weakened, and just kind of weathering and erosion and stuff, it became unstable, and then, you know, just whatever, right, trigger stuff, like a big chunk of that like broke free and came down the channel. But yeah, we kind of had like a nice debate with that amongst NTRP last year, because lots of people are interested in the electron mud flow, but everything I can see from Tom Sisson again, who did a lot of that research, they just don't have the evidence of volcanic activity then. So that's kind of why the waffling around, like, yeah, it can actually be caused by multiple things. Yeah.
Well, that kind of brings up the question I have about the warning. I mean, you're saying typically for an eruption, you might have weeks or months, but let's say you have a mud flow that's not related to eruption, like let's say it happens on the White River and you're camped in the campground. I mean, that seems like the biggest risk because you may not have any warning at all. Is that
exactly.
true?
It can get really dicey, and that's what makes us, you know, nervous. And I know on some of my talks, it's like we often say, it's like if you hear a rumble that sounds like a freight train, get uphill just about as fast as you possibly can.
Yeah.
Because that's what's going to save you. But it's like, yeah, especially in the park, there wouldn't be that much warning. If I remember right, these can go about like 40 miles an hour. So it's like there could be a bit of warning for the towns outside, but not that much within. But yeah, that's a big part of the concern.
Yeah, I wanted to reiterate what you just said, you know, because you were wondering yourself, yeah, it's like hearing a freight train coming down a valley, you know. One time I thought I was up, you know, in the Tahoma Creek area, I was up, you know, Fish Creek hiking up the road there. And something did come down, you know, not a lot at the time. And it was way back in the 1990s, but I was running back to the car, you know, and I was running as fast as I could.
And I would too.
You know, and this was already, you know, since all of the stuff had been washed out, you know, parking, built the whole area back there and washed out one of the culverts back, you know, further back. But I ran back and now the water, you know, it didn't come up real high, but I had enough concern to get down in my car and get out of there. Because, you know, I could see trees, big trees, swaying. Yeah.
And so, I mean, I think that's the thing. It's like thinking about us reaching out with the public and stuff is just the more we can kind of raise like situational awareness. You know, there's never like a perfect solution. But, you know, like Paul was talking about the one in 2016, and, you know, like the people that are like, I'm afraid, and then they were standing there. The other thing I remember from that video was the road they were on, you could tell it was like freshly graded, and that was because it had been wiped out by a previous one of those glacial outbursts.
Yeah, I did a few studies on my own. The 1947 flow that came through Counts Creek, that area there, was that was weather related. It was related to a lot of heavy rain, you know, up above. The ones in the Tahoma Creek area in 73, or around that, the 70s area, were once again related to weather. And then there was another one in 2005 down the Van Trump one. There's YouTube videos of that one.
Yeah.
That was related to weather as well, heat, you know, and you calve off a piece of ice off an end of a glacier, it's going to dam it, and all that pressure is going to build up right behind it, and you know, eventually it's got to go somewhere.
Yeah.
Gravity's going to eventually take over, and it's all coming down, and it's just going to come down to a big mass, you know, and it's coming down. You know, at varying speeds, you know.
Yeah. Yeah, another question here.
I had visitors on a new Meadow Rover, and there's a visitor who asked, what did we learn about the Mount St. Helens eruption that are going to make us safer, or sort of like was asking sort of, and I didn't know how to answer that question, but it sounds like you might have some.
Yeah, especially, well, let me see if I can kind of just advance here. So kind of go here. Let me see, this is kind of like the Mount St. Helens scenario. So it's like partially the magma came up off center. One of the problems with Mount St. Helens was it was so symmetrical. People sometimes called it like the Mount Fuji of the Northwest. There was a lot of assumption that if it erupted, the energy would go straight up. And with this thing of the bulge that kind of developed on the north side of the mountain, and you can actually see it here, this like nasty looking volcanic wart on the side of it. I think most of us can look at it and it's like, that doesn't look right. That was part of what we were looking at and they were monitoring. But with that, I think there still wasn't kind of that recalibration of it's not going to go straight up, it's going to come out the side. And there was an earthquake associated with like the magma and stuff coming up in there. If I remember right, that was about like a 5.7 magnitude earthquake. And with that, you have this bulge is basically out of equilibrium, right? It's kind of like sticking off the side, just barely hanging on there. And then you shake the daylights out of it. That caused like this gigantic landslide. And with the water in there and this sticky, goopy lava, it was like a mad shook up champagne bottle. And kablooey, it blew out the side, and so instead of the energy going up, it went out the side and it impacted a much bigger area. So
Yeah, I heard movement had been like 7 feet per day, you know,
Yeah, it was big, but we did have a warning, right? Yeah, it's pretty crazy. Yeah, and so it's like when you do have it like blast out, you know, it came out to the north. Unfortunately, the David Johnston, the guy that the visitor center there is named after, he was a USGS geologist that thought he was in the safe zone, but wasn't once, you know, kind of the geometry of this thing changed. And then it kind of did the ash cloud that we've seen the pictures of. I'd say, you know, we have the lava dome. One of them I think is kind of it's a science and we learned from it. That I don't think got reported that much in the news was in the Caribbean and Montserrat, the Soufriere Hills volcano became active in the 90s. And it basically mimicked what Mount St. Helens did. Bulge on the side, all this kind of stuff. And some of our USGS geologists went there and, you know, red flags going off. We've seen this scenario before. And they evacuated the town of Plymouth and got everybody out of there like weeks before it blew out the side and turned the town to ash. So, yay scientists, we learned.
How long did it, you said there was that bulge, was that like over a course of years?
Weeks.
Oh, really? Oh, that
Yeah.
fast? Oh, wow.
Yeah. But yeah, I don't know exactly how many weeks, but yeah, I remember
No,
seeing that happen.
weeks in geological time is.
Yeah, that's very fast. That's
Yeah.
like the snap of the fingers, right?
Thank you.
Yeah. Any other questions before we wrap it up?
Do you have any reading suggestions?
Any what suggestions?
Reading?
Oh, reading suggestions. Ooh, that's a good question. I really didn't think about that ahead of time.
Well, if you think of one, you can pass it on.
Yeah, we can pass it along to you. We can see what we have there. Yeah, I'll have to think on that one.
What are you curious about in this moment? I mean, you're studying a lot and have a lot of knowledge. Is there a question you're particularly moving over right now, or?
That's a good question. I think it's one of those things, and who knows what will happen in my lifetime. You know, it's like we do have this thing where it's like sometimes we do get lava flows, we do get ash. I'm really curious what it does next. You know, and it's like that may be 1,000 years from now, so I don't know that I can answer it. But it's like I would love to learn how, you know, this kind of current version of Mount Rainier, kind of as it's getting older, what's it's going to be its character. You know, it's largely been kind of the ash fall and pyroclastic stuff and a little bit of lava here and there, but, you know, is that a pattern or is it going to break through and do something unexpected? And that's where my curiosity, the biggest part is right now.
And it sounds like there was a comparison with this volcano that you have pictured. Are there volcanoes that are sort of like, seem similar, and so there's sort of cross-study going on with them?
Oh yeah, absolutely. It's like I think most of the Cascade volcanoes, you know, a lot of similarities in terms of composition, setting, things like that. And that's really our folks at the Cascade Volcano Observatory, which got set up after Mount St. Helens, that you can go online and see kind of this is their monitoring, this is what's going on. So it's like we're collecting that data, and yeah, it's every volcano is unique, but at the same time there's some commonalities, and I think we're just going to keep on building on that. And the tricky thing is, you know, unlike Kilauea, which just seems to like go all the time and you're constant stuff, is the eruptions on a lot of these, you know, you're looking, it's like, you know, human lifespans and stuff, so it's a long-term kind of data collection thing. It's slower to get the science, but very important. Yeah.
Is there any research being done showing any evidence that there may be another volcano forming in the Cascades?
That's a good question. I don't know of any new ones forming right now. The question mark that I think of in terms of Oregon is down by the Three Sisters by Bend. That was an area where they were seeing some like bulging of that, like probably like 10 years ago. It kind of like started up and everybody's like, hold on to your hat. And then it kind of like simmered down like volcanoes tend to do. Kind of where that was kind of on the flank. It wasn't, you know, up on the volcano. It was kind of like lower down. So it makes me wonder, you know, would that actually build on the current peak, or are we gonna start doing something where it's kind of like a multi-peak thing, which is more like what Mount Shasta is? It's got all kinds of weird add-ons that happen there over the years. So that would be a curiosity there, but we'll see if and when it's gonna wake up and do anything. All right. Well, thank you again.
Great, well, thanks everyone for coming out. We do have a plan to put together a Google Doc with lots of other like supplemental training kinds of readings and book ideas, articles, maybe some videos, we'll see. So we're in the process of getting that ready, and when it is, we will send out the link to it. And we hope to have at least one more in-person training in a few weeks. We're in the process of scheduling that, so we'll keep you posted. And that one will be on plant ecology of Mount Rainier. So, yeah.
Are you going to be able to put these PowerPoints on the site you were talking about, or is there any
So
plans to do
this
this?
has been recorded, and that will, the link
Oh,
to
the
that will be
recording will,
sent out.
not the PowerPoint that you're going
I'm
That
happy
will be
to
up
share
to
my
the presenter.
to.
Yeah, seeing as how 90% of my stuff is borrowed from other people, it's only fair.
Yeah, and we can ask Paul if he's willing to do that, I imagine.
Great, thanks.
Yeah, great, thanks everyone.
Thank you.
And if a couple